Okay, so in this video, we're going to talk a bit about isotopes. So if we have an element, we know that if we change the number of protons we have, we change the elemental identity of that thing. Well, we talked about if we change the number of electrons we have, we're talking about different ions. Now we're going to talk about what happens if we vary the number of neutrons in our atom. So if we vary the number of neutrons, we have what we call isotopes. So Dalton was a tiny bit wrong about his atomic theory, the way he wrote it down. So he said that all atoms of a given element have the same mass. This isn't quite true now that we've figured it out. So remember, neutrons are the most massive subatomic particle. They're the biggest. So if we add or remove a neutron, we're going to notice that this happens. We're going to have a significant change in the mass. Remember, they weigh about or have a mass of about 1 AMU. And so if we add or remove 1 AMU, we're going to notice that that happens. We sort of account for this along the way in modern atomic theory. We don't just say Dalton's wrong and toss along the whole thing. We now know that isotopes are a variation of elements in atoms in an element. So isotopes of a given element vary by the number of neutrons, so they have different masses. So they've got different numbers of neutrons and have different numbers of masses. So I'm often going to talk about changing the number of neutrons. However, that's not really kind of how it works. It's just how it works well in English talking about it. So isotopes are naturally occurring. So it's just kind of when I pick up an atom of one kind, I'm going to have different isotopes depending upon which atom I'm picking up, basically. So I know neon has 3 different isotopes. So if I have a sample of neon, there's a chance I'll have some of the isotope that has a mass of 20, 21, or 22. I could have any of those 3. However, they all are still neon, and they're all still the same thing. Technically, we can shoot neutrons at an atom, try to get one to stick in the nucleus, so we could force an isotope to occur. But we're always going to be talking about in this class about naturally occurring isotopes. So if I'm talking about changing the number of neutrons, I'm just talking about comparing 2 different isotopes. Some elements only have 1 isotope, so they only occur with 1 number of neutrons, and then some occur with 2 or more. So again, isotopes are atoms with the same number of protons, but with a varying number of neutrons. So they have the same identity, they just have different masses because of their different number of neutrons. So basically, we're changing the number of neutrons in an atom. And remember that neutrons are electrically neutral. So having different numbers of neutrons does not affect the charge of the atom in the end. So if we're changing the number of neutrons, we're just adding and removing an electrically neutral subatomic particle, so we're not changing the charge of the atom at all. However, we do have different numbers of neutrons, and remember, neutrons are very massive, so changing the number of neutrons does change the mass of an atom. We denote how many neutrons we have using what we call a mass number. So a mass number is represented by the letter A. We have the atomic number, so the atomic number is represented by Z, and the mass number is represented by A. Yes, I know, that's confusing. You'd think atomic would be A and mass would be Z. No, atomic is Z, mass is A. It is what it is. But that A represents the total number of protons and the total number of neutrons in an atom. So mass number is number of protons plus number of neutrons. This in the last cut of the video, but I wanted to actually write it out as an equation for you. So the mass number is going to be the number of protons plus the number of neutrons. So this mass number includes all of the protons and all of the neutrons. In comparison to that atomic number Z we were talking about is just the number of protons. So your atomic number Z is kind of hidden in here a little bit. We call it Z. Z plus number of neutrons equals A, but I don't usually call them A and Z. We've got mass number as the number of protons plus the number of neutrons. So we have isotope symbols that we might write 2 different ways. I will always default to the second. I will never write them like this. It's very complicated to write them like this, and it's very hard to typeset them. So I'm always going to write them like these ones down here, but just so you know what they look like when you see them. Your mass number goes on top, your atomic number goes down below, and then you write the chemical symbol. So the mass number and the atomic number come at the front, and then the chemical symbol comes second. So again, we have 20 protons plus neutrons. We have 10 protons in neon. That's what it's showing you here. So we have one that has 20 protons and neutrons. We have one that has 21 protons and neutrons. And we have one that has 22 protons and neutrons. But we can see that we're not changing the number of protons at all. So here we must have 10 neutrons. Here we must have 11 neutrons. And here we must have 12 neutrons, because remember, if we changed the number of protons, we would no longer have neon, but this number at the top represents protons plus neutrons, so if I'm not changing the protons, I must be changing the neutrons. So here I have 10 neutrons, 20 minus 10 is 10. Number of protons plus neutrons minus number of protons, it gives us the number of neutrons. So 20 minus 10 is 10, 21 minus 10 is 11, and 22 minus 10 is 12 neutrons. You can write the same thing just like this. So you might write the chemical symbol, dash, and then the mass number. So this is the way you'll see me write it. It's much easier. It makes more sense to me because in the end, I really only care about the mass number because I can find the atomic number by looking at the periodic table, right? Z is the number on the periodic table, that atomic number from the periodic table. So if I have neon, I can just go straight to my periodic table and I can see that it has 10 protons. So it's kind of like extra to write out that top version of the isotope symbol. I'll always write down the bottom version of the isotope symbol. So here we've got one with 20, 21, and 22 for their mass numbers. Same thing. So these are denoting the same exact thing in both cases, just that this one's written in one form of an isotope symbol and this one's written in another. So just to be a little bit more specific, how you might compare these and look at that difference. Here we have those same three isotopes of neon, so 20, 21, and 22. We have those symbols written next to each other. They're both equivalent. They're both interchangeable. We see again that each of them has 10 protons, regardless of how we write the symbol. Because it's neon, neon has 10 protons. If it didn't have 10 protons, it wouldn't be neon. However, we see that our number of neutrons changes. So our mass number goes up, our number of neutrons goes up. So if we have 20 for our mass number and we have 10 protons, that must mean we have 10 neutrons, and so on and so forth. Well, we'll talk about this in just a second, but this is the percent natural abundance. So most of the time when we're talking about neon, we're talking about neon 20. If you just sort of say neon 20, I assume you mean, or if you just sort of say neon, I assume you mean neon 20 because I assume you mean the one we have the highest percent abundance for. But neon can also exist in the other two in just a very small amount. We wouldn't often see a neon 21 or a neon 22. We'll most often see a neon 20 atom in existence. Lastly, in this video, we're just going to work through some examples of some types of questions I might ask you about ions. Of course, you can see all of the examples and how I work through the examples in this PowerPoint as well. But here's just so you can hear me talk about it out loud. So if we're talking about an example number 1, an isotope symbol, what is the isotope symbol for chlorine with a mass number of 36? Pause if you'd like to write it down yourself first. However, I'm going to go ahead and talk about the answer. We'll look at it on the screen here. So if you're writing the chemical symbol, or if you're writing the ion symbol for chlorine with a mass number of 36, the way I would write it is just Cl, the chemical symbol for chlorine, dash 36. So the chemical symbol is Cl, and it already tells us that that mass number is 36. And the ion symbol is always the chemical symbol followed by the mass number. So we already have all the information we need. We can just go ahead and write Cl-36. If we move on to the second example, what is the isotope symbol for a carbon atom with 7 neutrons? If you want to work this one through before I talk about it, go ahead and pause now and resume. So if I'm looking at a carbon atom with 7 neutrons, I'm thinking about the fact that I'm trying to write the isotope symbol for it. So if I'm trying to write the isotope symbol for a carbon with 7 neutrons, the isotope symbol is made of the chemical symbol followed by the mass number. So if I have carbon, I know my chemical symbol is just a capital C. And then I have to figure out what my mass number is. So remember, mass number is number of protons plus number of neutrons. It tells me here I have 7 neutrons. If I have a carbon atom, I can look at the atomic number 6 for carbon on the periodic table. Carbon is atomic number 6. The atomic number is the number of protons. So if I have 7 neutrons and 6 protons, I have 7 plus 6, or 13 is my mass number. So my mass number is 13, so the isotope symbol here is C-13 is how I would write it. We'll work on example number 3 now. So example number 3 says, how many neutrons does an iron 58 isotope have? And how many protons? So go ahead and pause to work on it yourself and resume for my explanation. So iron 58, if we want to know how many neutrons this isotope has and how many protons, we're going to need to think about the fact that we have iron first and foremost. So I can immediately figure out how many protons it has, right? So how many protons does this have? Well, and Fe, or any iron has 26 protons. Iron has an atomic number of 26 on the periodic table, so it has 26 protons. So that means I can answer my second question right off the bat. Iron has 26 protons. And then I need to figure out how many neutrons it has. So remember, mass number is given as 58. If the mass number is 58 and I know I have 26 protons, mass number is number of protons plus number of neutrons. So if I take mass number minus the number of protons, I can get the number of neutrons. So if my mass number is 58 and I take out my 26 protons, that must mean I have 32 neutrons. So Fe58 has 32 neutrons and 26 protons. Work through number 4, very similar to number 5. So we're going to figure out how many neutrons and how many protons a C14 isotope has. So if we're looking at a C14 isotope, we can see that that's a carbon isotope. So we can immediately figure out how many protons it has. I'm going to go to my periodic table. I'm going to look up carbon. Carbon is number 6. It has atomic number 6, so that means it has 6 protons. So I know my isotope has 6 protons. And I can use that information as well as the mass number to figure out how many neutrons I have, because mass number includes both protons and neutrons. 6 of my 14 things are protons, which means the rest of them must be neutrons. So I must have 14 minus 6 protons, which is 8 neutrons. So 14 minus 6 is 8, so we have 8 neutrons. Our mass number is both protons and neutrons. We're going to take out the 6 protons we have. So 14 take out 6 is 8 neutrons. Okay, so that's number 4. So we're going to switch gears and we'll do examples 5 and 6, which are a little bit closer to each other. So example number 6 says, if an isotope has a mass number of 39 and has 20 neutrons, how many protons does it have? So go ahead and pause and resume if you want to hear my thought process. So if an isotope has a mass number of 39 and it has 20 neutrons, pretty easy to figure out how many protons it has. Mass number is protons plus neutrons, so if I take away the number of neutrons, from the mass number, I'll have the number of protons I have. So in this case, my isotope would have 39 minus 20 protons, which is 19 protons, which if I look at my periodic table, means it's an isotope of potassium, because if it has 19 protons, that must mean it has an atomic number of 19, that must mean it's potassium. And so the example I've given you is an example of a potassium isotope. However, do I think it's a real potassium isotope? No. Oh, actually it is. It's the most abundant potassium isotope. Magic. So that's an actual isotope of potassium that would have 39, a mass number of 39, so that's 39 protons and neutrons together, and it has 20 neutrons, and that leaves us with the fact that it has 19 protons. 39 minus 20 is 19 protons, which indicates to us that it's potassium. So for the last one here, example number 6, we're going to do a very similar example. If an isotope has a mass number of 27 and has 14 neutrons, what element is this an isotope of? So we already kind of did this in example number 5. We'll do it again here. So if I'm looking at an isotope that has so go ahead and pause. And now you're going to hear my thought process. So if I'm looking at an isotope with a mass number of 27, and it has 14 neutrons, I know mass number is number of protons plus number of neutrons, so I can subtract out my number of neutrons to get my number of protons. So if I have a mass number of 27, I can subtract 14 neutrons, which means I have 13 protons. So if I have 13 protons, that means I can go to the periodic table, I can find the element on the periodic table that has the atomic number of 13. If it has an atomic number of 13, that means it has 13 protons. So I'm using my number of protons to figure out which element it is using the atomic number. So in this case, example number 6, our element is aluminum, because I figured out my number of protons, and aluminum has 13 protons. So again, those are some examples of how we might work through some isotope problems, some questions I might ask about isotopes. And you can see all of the answers with those explanations on the next slide as well. So I just want to give you one quick summary of the difference between elements, isotopes, and ions. So remembering that elements are defined by the number of protons. So if you change the number of protons you have, you change the identity of the element. Ions are created by adding or removing electrons to atoms. They are charged particles. If you have more electrons than protons, you have a negatively charged ion, an anion. If you have more protons than electrons, you have a positively charged ion, which is a cation. And in ions, the mass number doesn't change, nor again does the number of protons, because we have the same element, we're just adding a charge to it. When we're talking about isotopes, they're naturally occurring atoms with different numbers of neutrons. Different isotopes of the same element have different masses because neutron masses are large. So if we remove or we add a neutron, we're definitely going to feel that mass change. So in isotopes, if we just have a neutrally charged isotope, charge does not change, and the number of protons does not change. So it's just a quick summary of the difference between an element, an ion, and an isotope. So ions and isotopes are variations of elements, but elements are always defined by the number of protons you have. So just a quick summary of how those are different, and that is isotopes.